So good afternoon, everyone. It's a pleasure to be here and to talk to you a little bit about Franklin Chang Díaz's career, his 7 space flights. That's a record there. And then about his post-spaceflight career in which he has tackled the dual problems of trying to find a faster way to get to Mars while also tackling some of the problems here on Earth, particularly energy and climate change. And so I think really probably the best thing to do would be to jump right in and talk to Franklin kind of about his early life. But first of all, let me just welcome you, Franklin, and say good afternoon.
Good afternoon there, Eric. It's a pleasure, and it's a pleasure to be joining you in this conversation.
Well, good. Well, thank you. Franklin and I have known each other for a long time now. It's always fun to talk to him and see what he's working on. But I think where we ought to start, Franklin, is maybe with, when you were a kid, obviously it takes a driving passion to get into a career like you got into. So maybe, you grew up in Costa Rica. What influences were there that got you interested in space?
Well, I wanted to to use a few images that I hope you are able to see.
Yeah, we see them.
This goes way back. I don't know if you remember. Well, I know you hadn't been born yet, but in the 50s, of course, the space age really began, and I was a young boy in growing up in Costa Rica. This is an image of our early family, 1958, in Costa Rica. Later on, we had, 2 more brothers came along. 10 years later, my parents decided to start production again. So 2 more brothers. But at the time, there were only 4 siblings, and I was the only boy. And Sputnik had been launched in 1957. And that was just the ignition point for a deep interest in space. And so that, took me to dream about space and someday, turning into an astronaut, which I thought I could do. Spinning up ideas, and then I became a teenager in the 60s, 65. I remember that this image here is an actual rocket that we built from scratch for a science fair. And we actually had a little mouse that we put inside a little capsule with a little parachute. And we launched that thing, and it went up to about a couple hundred meters or so, and the mouse actually survived. And we took it out of the capsule, and it jumped away, and then we never saw it again. So that was the early days, and of course, as time moved forward, I had to make a decision as to what to do. And I wrote a letter to von Braun, who was the father of the American sort of modern rocket program. I didn't get an answer from him, but I did get a letter from NASA, which you can see here. And of course, I didn't speak English at the time, so I couldn't really understand what the letter said, but someone translated it for me. And it was interesting to see the underlined, somebody had actually underlined the last sentence in the second paragraph, which basically said that careers with NASA were limited to American citizens only. And that, because of my poor understanding maybe of the language, meant to me that I just had to come to the US. And that's what I did. In 1968, I packed my bags, got my dad to buy me a ticket to the United States, got some distant relatives of mine who lived in Connecticut. They were willing to put me up for a while. And in those days, it was a lot easier to immigrate to the US. And so I came here with a one-way ticket. $50 and try to learn English. That was my first job, was to try to learn the language, which I did. Went to high school again. I had already graduated from high school, but decided to go back to high school so that I could learn the language. Got a scholarship to the University of Connecticut, but also in that following year, 69, Neil Armstrong landed on the moon, and that made, it made me feel that I was a little closer, not as far as I'd been before. I joined the freshman class at the University of Connecticut in 69 to graduate in 73 as an engineering student, but I really became fascinated by physics. And so I kind of became an engineer student working really on experimental physics. And I did a lot of work, doing all of that, learning all the skills of an experimental physicist that eventually would take me to grad school. And grad school was MIT, 1973. Interestingly enough, the space program had been canceled by President Nixon, and the shuttle program had not begun yet. And a lot of NASA engineers were laid off. And I remember my professors in the university would tell me, Franklin, don't even think about going into the space program because you're never going to get a job. Because there were thousands of aerospace engineers out of work, and I'm glad I didn't pay attention. But I decided to take a little detour, and I went into thermonuclear fusion, which I thought was very relevant for the future of space transportation. Nuclear power for me was an essential ingredient that had to be in there for deep space exploration. And so I went into the field of plasma physics and fusion. And that took me through the 70s. And then in 1980, after a couple of tries, NASA had begun the space shuttle program. And then after a couple of tries, I was selected in the 9th group of astronauts in 1980. And I'm sitting right here on the bottom left, right next to this guy who became a really good friend of mine and also became a NASA administrator. And it's amazing how these things happen over the years, but we were all very young. And then began flying, flew 7 missions. Imagine, and the wildest of my dreams that I would fly that many flights. But for some reason, I was at the right place at the right time. I was flown multiple times, got to do a lot of work in the early shuttle flights, flew to the Russian Mir station, spent some time there, supported the construction of the International Space Station, and basically saw how we humans have become a spacefaring species that have lived in space now for the last 20 years without interruption. And the world has changed. That Sputnik satellite that was the only floating man-made object now we got hundreds of millions of objects orbiting the Earth, making it extremely busy, and also a tremendous business opportunity that is there for the taking. And space has become a place of business, a place of work. And that's what I'm beginning to see that we need to focus on for the future. The planet has become also overstressed, and therefore the issue of climate change is front and center. And we have to care of, for this one spacecraft that we inherit, the Earth. And so space and climate change and the future energy matrix of humans, they're all intertwined. They're all interconnected. So for us in space, the transportation problem was fundamentally something that needed to be addressed before humans could really become truly a spacefaring species. And that is chemical rockets, which have done very well over, since the end of World War II, all the way to the moon landing, basically suffered from a fundamental, problem, which is that they take too much fuel. And the rockets that we launched have a very low payload capacity. So it's a little small fraction of the stack that you put on the launch pad actually gets to its destination. And so we want to change that. We want to go to electric rockets, just like we are moving to electric transportation on Earth, on the surface of the Earth. We also want to move to electric transportation in space. And this is one of the things that we're doing in our project, our company. The Bessemer engine is a high power electric rocket that will transform the way we move around in space, and we make it a lot more efficient and economical. So covering the full spectrum of applications. I mean, this is a technology which, sort of marries propulsion. It marries the technology of thermonuclear fusion, plasma physics. And this rocket is Texas grown. It was developed here in the state of Texas, and it has been under development by our company ever since the early 80s. This is an actual video of the rocket firing recently. This is 100 kilowatts of plasma controlled by a magnetic field and energized by electromagnetic waves. The temperature of this plasma is close to the temperature of the sun. Is 4 to 5 million degrees, and this means that the rocket uses very little propellant, very little fuel, which is the crux of the problem that I mentioned earlier. But this is the kind of technology that we're doing right here in our backyard, right here in the city of Webster, just a few miles from the Johnson Space Center. We have gone through a very interesting maturation process. I mean, this is essentially a project which has been mostly privately funded. We left NASA in the early 2005 to form the Astra Rocket Company, and then began to bring in private money. And this is another change that has occurred in space. The private investment, the private component has been not negligible anymore. Actually, is one of the most important pieces of the financing going on, driving space commerce and space activity. So we have moved the technology readiness of the rocket. We are just about to graduate from TRL 5, or Technology Readiness Level 5, and move into what we call the proto-flight environment, where we can actually build an engine that can fly and be demonstrated in space. This is what we are hoping to do in the next 5 years or so, starting with next year. So what do we do with it? Well, we do everything. We can do a reboosting of stations. We can do orbital debris, cleanup of all the space lanes that have become so crowded, servicing satellites, and also move deep space probes, deep into space. Now, all of this is electric. First, we will be using solar power because we're close to the sun. The Earth is close enough to the sun. But when we go further away and we need a lot more power and we want to transport humans, we will go into nuclear electric power, which will drive rockets at not hundreds of kilowatts, but maybe tens of megawatts. Now that's a whole nother story. And this is what really makes it exciting, to need to move into space in a way that you could have the entire solar system, you know, at your disposal, that you can plan missions to any point in the solar system within a human reasonable time, so that you can come back and tell the story or do something with it. So now this is the promise as we develop nuclear power. This is the trip time. You can see a plot of the trip time to Mars as a function of the power of the reactor. And you can see as the power of the reactor goes up, and also the technology of the nuclear power plant gets better and better, then the time that it takes us to get to Mars gets down to very interesting numbers, like, you know, a couple months. Now, going to Mars in a couple of months would be really neat. And this is, this is what we really need to shoot for. These ships will be interesting looking. I mean, they will not be ships that land on Earth or land on Mars. There will be orbiting ships, and only the lander would actually land on Mars. You see the little lander here. These are big ships. They're propelled by plasma engines, nuclear power driven by nuclear reactors, and using hydrogen. And then again, you can see the hydrogen technology, how it's beginning to come into play. All the work that we're doing on hydrogen on Earth now begins to play a role. Hydrogen becomes the propellant for the plasma, and hydrogen will be stored in these containers, which will be also serving as shields to protect astronauts from the radiation of space. So we will have a primary shield for radiation, which will be hydrogen, which is the best possible shield that there is. And then inner to the structure, we will have a magnetic shield generated by superconducting magnets. And again, here in Houston, in Texas, a lot of interesting technology development in the area of superconductivity. Again, the state and the city is pioneering these kinds of technologies that will be useful, not just to go to Mars, but also to transform the energy infrastructure in the future. So these are the kinds of things that we're contemplating for not too far into the future. In fact, we for this notional mission that we've looked at, we already have a departure date, May 20th of 2035. And this mission will take us to Mars in a 95-day flight. This is not the best we could do, but certainly something that would be interesting to do as a get started. So that's the space portion of what we are doing. But then going back to Earth, we have a small operation in Costa Rica. And what we want to do is use Costa Rica, which is a very small country, as a great laboratory for testing these kinds of new energy technologies. We focus on carbon-free hydrogen infrastructure, design, development, and integration, maintenance, and all of that. And what is the problem in Costa Rica? You know, Costa Rica has a tremendous opportunity. Costa Rica has no oil like, you know, Texas does. So it imports everything for transportation. But Costa Rica has a very clean electric matrix. And Costa Rica has a lot of sun and a lot of wind. And if we could transform all of that solar and wind power into hydrogen and store the energy in that way, we essentially have 3 times available what Costa Rica needs to run itself. So we would like to demonstrate Costa Rica can become a carbon-free country. And if Costa Rica can do it, many of the countries in the surrounding area can do it. And I believe this is something that the whole world can actually accomplish eventually. It will be transitional. So this is how we've started. And back 10 years ago, we began with this hydrogen activity in the country. And by November of 2017, we had the first demonstration of an ecosystem of hydrogen fuel cell electric transportation with the first urban bus that was deployed in the country, in the northwest of the country, powered entirely by solar, wind, and hydrogen fuel cells. You can see here the whole grouping of all of the hydrogen stations throughout the whole world. This is a growing number everywhere, but in Latin America, we're the only ones, and we're the pioneers right now. I am hoping that soon the whole southern cone and southern section of the planet will be covered by hydrogen stations, but it hasn't happened yet. We're trying to make that happen. So this is the infrastructure that we're moving to right now. We can power buses, and we have now deployed cars for the first time. The first entry of sedans, fuel cell sedans in Latin America happened in Costa Rica in 2018. And we are now implementing fast, what we call H70 refueling, so that we can refuel the cars in a matter of minutes and obtain ranges of the order of 550 kilometers. So this is very, very interesting for a country that small. So in summary, 217, first fully operational hydrogen energy production and ecosystem in Costa Rica. In 2018, the first fuel cell sedans were introduced in Latin America. And today, we operate the first fully renewable hydrogen transportation ecosystem in all of Latin America. And this year, we will go to state-of-the-art H70 fast refueling capability, also the first time in Latin America. So that, Eric, that gives you a feel for, you know, the whole journey that we've had all this time. And I will stop talking here and maybe start the conversation.
Well, thank you. That was, we went from 1950 to 2020 and from Earth to Mars and back in 20 minutes. So that's pretty efficient. Thank you, Franklin. I'd like to unpack some of the things you said a little bit and go back. I think you were about 7 years old in 1957.
That's correct.
When Sputnik happened. And do you actually remember that or sort of?
I do. I do remember, not as that something that came to me, but it's something that my mother, you know, informed me that there was a man-made star that you could actually see this in the early, you know, early morning or sort of early evening. You could see this star go by. I looked for it, never saw it, but it was fascinating to me that there was something like that could happen.
And was it truly that this sparked you to sort of start looking up at the skies? Because, you know, in high school, you're clearly doing a lot of really complex things with rockets for high school.
Well, it was that, but, you know, Eric, in those days, all boys of my age wanted to be astronauts. I mean, we all wanted to fly in space. This was just the thing to do. You know, space was the thing. And you know, I remember I had my own spacecraft. You know, it was a box. It was a cardboard box. And, you know, we got in there with my friends and my, you know, cousins, and we would go through a whole countdown and, you know, fly into space. So this was nothing new and nothing unique. You know, I was just a regular boy. I was nothing special.
So you wrote to NASA in 1967. Did you also write to the Soviet Union, their space agency?
No, it's funny because, you know, Eric, in those days, you know, there were only two players in this game. It was the Soviet Union and the United States. And, you know, to me, the Soviet Union was just a, you know, a faraway, mysterious, you know, sort of cold and and dark country. Maybe that was also fueled by the, the propaganda that we had, post during the Cold War. I mean, we were bathed by the American propaganda as well. So, and also, the country was very, Costa Rica was very friendly to the United States. President Kennedy actually came to visit Costa Rica, and it was a completely different flavor from the Soviet Union. So,
yeah, I find it pretty remarkable that you wrote to Wernher von Braun in 1967. Right in the middle of the Apollo program, when they're trying to get all of this stuff off the ground. They were right in the middle of launching the Apollo. The Apollo rocket, Saturn V, for the first time, and trying to do the Apollo 1 mission, and they wrote you back. I mean, that must have been pretty cool.
Yeah, I was, when I received that envelope from NASA, I mean, my whole day stopped. I mean, it was like I got something from God. I mean, something that I wasn't even, I was so in such a state of emotion that I didn't even want to open it. And it was almost a religious moment. And all it was just a package full of brochures with that letter that I showed you. Yeah. And it didn't really say much except that, most likely, you couldn't do it because you have to be a US citizen. And the way I misunderstood and thinking that what they were telling me is, come on over. I did.
So you came to the United States in 1968, which was this really tumultuous year. Not unlike 2020 in some respects, although certainly there was no pandemic, but the United States was pretty divided, contentious election, civil strife. And I'm just wondering, sort of coming from Costa Rica into this country where you didn't speak the language, kind of what those first weeks and months were like in this new country.
I found a country that was totally different from what I had thought it was. I found a country that was tearing itself apart I went to a high school in Hartford that had all kinds of disturbances and problems, racially motivated. I was, discriminated because I was Latino. I didn't realize that Latinos were discriminated in the United States, that just didn't come. And, the war in Vietnam was in full swing, and the young people were burning draft cards, and many of them were coming back from Vietnam in body bags, in plastic bags. And there was a tremendous, anti-establishment, fervor. And the country was, had just killed Martin Luther King, Bobby Kennedy had just been assassinated. And it was like this country was tearing itself apart. But then we landed on the moon. So it was almost like cold and hot, and it's one of the things I most admire about the American society is its ability to sort of reinvent itself. Mm. It's one of those things that no other country that I have ever seen has the capability to do, is to reinvent itself, to kind of air out all this dirty laundry for everyone to see, and sort of self examine everything out in the open. And I just think this is something we need to preserve.
So then you go off to the university and you're interested in physics and engineering, and then as you sort of get to the end of the college, NASA is trying to reinvent itself as well, because the Apollo program is winding down, right. Funding is being cut, and at that point, as you're coming out of college and you're hearing, well, maybe you shouldn't do this, you shouldn't try to work for NASA, did that diminish your dream of becoming an astronaut, or did it burn sort of as brightly as ever at that point?
Well, the whole astronaut thing was a dream that was very much alive, but it kind of wound down a little bit because I was interested in energy. You know, there was an energy crisis in 1973, and the space program was pretty much you know, almost dead. You know, that nobody heard anything about it. Apollo missions had been canceled, and nuclear power was in the upswing. And you know, I thought that this was the future, and I almost forgot all about NASA until 1977, when the first space shuttle, the Enterprise, began to be flown out at Edwards Air Force Base. And you know, you see this majestic bird, you know, that was getting ready to go into space. And I thought, man, this is the beginning again. And now I was in the US. I was a US citizen. I was in really good shape. You know, I had all the ingredients, but I was not a military guy. Never have been, never been interested in the military. But I figured that someday astronauts would be scientists. And sure enough, that's exactly what happened. You know, NASA began to select astronauts that had the scientific backgrounds. And
yeah,
so,
that was one of the really great things about the shuttle program. It was really a democratizing process for who got to go into space, because you had women, you had scientists, you had people from all different cultural backgrounds, and it certainly, you fit a lot of that. I mean, you were kind of fit right in with that group.
Yeah, I think so, and I am, you know, grateful for all the things that were going on in the United States in a social environment, which allowed me to have the opportunity to do this.
Yeah.
If it had not happened that way, all my dreams would be for naught.
So you flew 7 times, which I think is tied for the most times anyone has gone into space. Why did you get to fly so often? Was it because like you were like Peggy Whitson, like the Energizer Bunny, just sort of getting every task done, or what? How would you explain that?
Well, I don't know. You know, I've asked Mr. Abbey that question, and I think he basically said, you know, is the right man for the job. The job needed to be done. The missions that I flew, they all had a certain feature that was sort of unique. You know, my second flight was the launching of Galileo, which was a nuclear powered vehicle to go to Jupiter. And you know, they felt that my knowledge of nuclear power was important, and I guess maybe that was one of the ingredients. Then the other flights I flew, the tethered satellite missions were very heavy on plasma physics, you know, electrodynamics and plasma physics. And I think that also had something to do with my, you know, my work there. And I flew the first mission of the AMS experiment, which right now is on the space station. And I think that they just felt my work in magnets and superconducting magnets had some important features to it. I don't know, Eric. I'm trying to really try to understand it myself, but I'm certainly not complaining.
Well, you must have done something right, because I know if you don't get to go back. So
I tend to get along with just about everybody. That's one thing that maybe also is important.
Yeah. I think you've told me this before, but didn't the inspiration for the plasma rocket that you talked about come while you were in space? Or tell me about sort of where you first began thinking about using that technology to potentially go faster and more efficiently through space.
Well, the inspiration came from my work in fusion, particularly the type of fusion machines that were open-ended, what they call magnetic mirrors. And these devices suffered from a problem that the plasma wouldn't stay in them because they have holes. And you know, the plasma would escape out of one of or two ends of this magnetic sausage-like structure. And I figured, well, man, it makes a pretty good rocket. And that's kind of the way it began to brew into my head, and of course later on working at NASA, I began to understand the importance of fast transportation and the importance of high efficiency propulsion, because we were just, the rockets just used too much fuel.
Yeah.
And, we need to increase the payload capacity. This is all there is to it. So I still feel that way.
So, it's interesting to me, like there seems like there's a common theme here. It's sort of more efficiently using energy, in space, more efficiently using energy here on Earth with the hydrogen project in Costa Rica. And to just sort of wrap this all up, sort of about this conference about, Houston and energy and climate change, I'm wondering, you're pretty good at sort of integrating these solutions. And so I'm wondering what you think, you've obviously lived in Houston for decades. What do you think sort of, if you were become the czar of climate change in Houston, in the energy capital of the world, what are some ideas you have for sort of addressing these issues on a local scale?
Well, we have to continue to promote, solar and wind. When you really look at this, the whole planet runs on solar power, and even wind power is solar power, and even hydroelectric power is solar power. So it's all solar power. The only thing that's not solar power is geothermal power, which is most likely nuclear power, coming from the center of the Earth. But really, the planet runs on solar power, and we need to get at that source of energy right at the source. Right now, what we're doing is we're going through very complicated gyrations. In fact, we go and get it from the bottom of the Earth, in the form of oil and gas. But that's really solar power that has been stored for millions of years, but it's still solar power. It came from the sun. So I think Texas and Houston, has all the ingredients to make all these things and connect all these dots and make it all work. And I am, I'm very optimistic about what we can do here.
Do you think Houston has the power to sort of transform from being so focused on fossil fuels to a solar economy? Certainly we have lots of sun in Texas, but old habits are hard to break.
It's hard, yeah, but it's not a technical problem. I mean, this is maybe a social economic problem. But I mean, Houston, for example, here in the east Texas, we have the largest salt dome caverns where they store large quantities of hydrogen. I don't think there's very many places on Earth that have that. So Houston has a lot of hydrogen already, and has a lot of wind, and all of that could be converted into hydrogen. My sense is that we have to look at hydrogen economy not just as a hydrogen economy, but also the oxygen economy and the water economy. Because when you make hydrogen from solar power, electrolysis, you're making oxygen too, and a lot of it. And when you consume hydrogen and make it into electricity, you're making pure water. And pure water is a real scarce resource, which will be even scarcer later. And I remember when we flew on the space shuttle, that's the water we drank. The water from the fuel cells.
Yeah.
It's perfectly good water. In fact, we had so much water that we had to dump it overboard. And sometimes we had to store it in plastic bags so that we can give it to the Russians because they didn't have enough water in the Mir station. So this is really telling us something.
Yeah. So we've got just a couple more minutes left, and I think we're going to open it up to questions, Q&A. And so some of these are starting to populate in the chat. And so I'm going to just start asking you questions from the audience, Franklin, if that's okay.
Sure.
The first question comes from Pat and asks why the trip on your graphic was so far away. I talked about a date of 2035 for Mars. Why it's 2020. That's 15 years away. We went to the moon in less than a decade. Why would Mars be so far down the line?
Yeah. Well, the reason is that it takes time to get this technology, and this is one of the reasons we have to go back to the moon. When we test, Eric, you've been to my facility here. We have a vacuum chamber, and we test the engine in a vacuum chamber. But the engine that we have is only 100 kilowatts. It's about the power of your car. But when you have a nuclear electric power engine at maybe 10 megawatts, there is no vacuum chamber on planet Earth that can allow this test to occur. So where are you going to test it? Well, you're going to test it in space. And most likely you're not going to do it on the space station because you will blow the space station out of orbit. You're going to put it on the moon. The moon is the place where we're going to be testing the big power plasma engines that we will need to get to Mars and beyond. That's why the moon is so important. And so, yeah, I mean, it takes time to do all that. It's a homework that we haven't done, and developing nuclear reactors to generate that kind of electricity is homework that we should have started 50 years ago. We didn't, and now we need to get moving on this. Hopefully we will start.
So NASA's current plan is to try to send astronauts back to the moon in the mid-2020s and then eventually go on to Mars. It sounds like from your answer that you think that the current plan the agency has is a pretty good one, the Artemis program.
Yeah, I mean, to me, the moon is a waypoint to Mars, but is a necessary waypoint. There's no way to do it and bypass the moon altogether, at least not in a sustainable way. So to me, it's very important that we do the moon and we learn to live and operate on the moon before we embark onto Mars. And I think that the private sector has a lot to play here as well.
Yeah, I think that's one of the attractive things about the moon is that it does have so much commercial potential. One of the things that I think the greatest resource the International Space Station offers is it's a test bed for microgravity. So it's a place to test how things behave when there's no gravity. On the moon, as you talked about for Vasimir, you have much less gravity, 1/6 of its gravity, but you have some gravity, but you have a vacuum, right? And so you can do all kinds of experiments in a vacuum like that, right?
Well, rocket engines that have to work in a vacuum, they have to be tested in vacuum, and certainly plasma engines have to be tested in vacuum. So you can imagine a facility on the moon where you just have a airlock and you put the engine there and you open an outer hatch and you drive the engine out on rails out to the open air, or the open vacuum. The open vacuum. And then you fire it there, and you got plenty of solar power if that's the power that you need, or you can have a small nuclear reactor there. But we can do it with solar power. There's plenty of sun on the moon too. And that's one of the reasons it's important to develop the hydrogen economy, because there's water on the moon, and we'll be using electrolysis of water with solar power, just the way we do it on Earth, to produce hydrogen and oxygen for the astronauts also to breathe, and also the water that we're going to need to drink. So, all of these technologies that we're developing here are going to be necessary on the moon.
So finally, if I could just maybe mash this up into one question that brings space and energy together. How do you feel about the idea of space-based solar power? The idea that you would put some kind of reflector or solar collectors up in space where there is no atmosphere or anything to interfere with it. You could get 24 hours a day solar energy and then beam that somehow back to Earth. Do you think that is the ultimate source kind of harnessing the solar energy you talked about? Or are we better off just sort of building better solar panels here on Earth?
I think we're better off building the infrastructure right here on Earth. I mean, the good Lord has already distributed the power pretty nicely, so everybody's got plenty of sun. And if they don't have sun, they got wind, and wind is sun. So, it's all, the solar energy is well distributed. Now, what solar power satellites are good for is to power other satellites. You can imagine an upper power station, say in geostationary orbit, powering satellites below, with beams, because you don't have an atmosphere to interfere, you see? And that would make those satellites a lot simpler and cheaper.
Oh,
And
that's
all
great.
you have to do is maintain the power station. So this is an idea that is almost a derivative of this idea of the solar power stations, but they're not needed for the Earth. They're needed for the infrastructure above the Earth.
Well, thank you very much, Franklin. I want to thank you for the time and sort of, I think you've given us a lot of ideas to think about sort of, the future energy economy with your perspective. So I really appreciate it.
And Franklin and Eric, I just want to thank you for really a fascinating way to end the conference. And Franklin, there were lots of boys in Costa Rica who dreamed of flying in space, but there was only one who did it. And you are an amazing individual for all that you've accomplished and the vision you have for what you want to accomplish, both for the space program and for energy. Is just incredible. And I think what you did nicely is you drew the link between the two and why this should happen in Houston. So
thank you. I owe all of it, or most of it, to a great nation that opened the doors for me and made it possible.
And we do a lot of work on immigration at the center as well. And I think you're just a shining example of why we want to do that and continue to do that work. So thank you for all you do, and thank you for being with us today. It was a really fascinating talk, and maybe you'll have us all out to see the engine when you hit TRL 6. We're looking forward to it because we have no doubt that it'll be there shortly.